So my name is just a little bit of introduction about myself. So my name is Suresh Purini. I'm a faculty member here in IIIT for more than a decade. I am in computer systems group. I work in compilers, computer architecture, distributed systems. Have varied interest, and these are some of my research interests. I taught computer discourse last year, and so teaching this course again this year. Yeah, so that's all about me. I love to play sports, any kind of sport, do yoga, meditation, all these things I love to do. Gaurav has a question. Do we have to make an account with our IIIT IDs? It's already there. No? You have a IIIT account, right, Gaurav? No, you don't need a Zoom account. Yeah, it's okay. Yeah, but having your name is good so that we know. Shruti is asking, why am I not using Teams? No problem, no problem. So okay, my question, why do you want to use Teams instead of Zoom? Yeah, Zoom it comes up on the calendar. So, but for me, I did a bit of study last year when I was about to teach online for the first time. Zoom is very simple and cleaner, and many things I am able to, as you see, go through the course. We will be doing some things like I want to annotate my whole screen. So different kinds of stuff, and all those things are very, very versatile and nice to do in Zoom. So after good amount of thinking and testing, I chose Zoom because I wanted to use, today I logged in using Mac, but otherwise I want to log in using my Linux machine, and Zoom on Linux, where I can share the whole desktop, annotate. It's a very, very powerful way of communicating. So that's the reason I chose Zoom. How are you all feeling? You're all doing good? Okay, nice. So yeah, good. So yeah, so few things. You don't require any kind of background to do this course. It's very, I assume, zero background. So all of you are good. Some of you may have prior programming experience and some of you may not have. But I assure you, by the end of this course, all of you will be more or less be the same. In the sense, the learning objectives are appropriately set so that all of you get good knowledge and experience in computer programming. So for the first 2-3 weeks, if you see some students are ahead of you, or even for the first 1 month or 2 months, some students are ahead of you, don't feel scared, don't worry. It's perfectly all right. Okay, so second is it is better to have Linux on your system. Better, it's not compulsory because all the courses assume that you have a Linux on your system. Yeah, if you have virtual machine, you can have a virtual machine. That's okay. Mac is also all right. If those of you who bought MacBooks, that's okay. MacBooks are very, you can, that's fine. If you have a MacBook, don't, it's all right. Yeah. But don't stress out if you are not able to get Linux going on your system. You can still survive using Windows, at least for the first semester. Maybe second semester onwards, for sure you have to switch to Linux maybe. So just want to check, so are there any CSE students here in this group? CSE, CSD? CSD, right? Yeah, okay, ECE? You put ECE, type in ESE, yeah. ECD? Okay. CND? CLD? Okay. CHD? Oh, good. So it's a good mix. Nice, very nice. So let's get started then. So anything you want to ask now, or shall we start? Okay, great. Nice. So in today's lecture, we will try to get some level of understanding on what constitutes a computing system, a very, very high level of understanding. I would like you to keep in mind that this is a high level picture, and there are many details which naturally you get inquisitive, and so while I answer some questions, I kind of defer answering many questions because we get into details and we go in a different direction. So try to get the big picture in today's lecture. So that is the objective of today's lecture. So that's why it's a 10,000 feet view of computing systems. So if you take any computing system, it consists of hardware and the software. So hardware is, like, for example, if you are working on your laptop now, what you can touch and, through your fingers, what you can see, that is the hardware. And then there is the software, like, for example, the Zoom software that you are using to attend this lecture. It's an example of a software. It's a software that can run on your laptop, on your desktop, perhaps even on your mobile phone. So your mobile phones are also very powerful computers. You end up playing a lot of games on your mobile phone or use other applications like Instagram, Facebook, maybe WhatsApp, whatnot. So all these are software applications that they typically run on your mobile phones. And then there is a third kind of computing system which we frequently interact with, which we frequently use, but we are not completely aware of it. That is, whenever you ask Google something, a tremendous amount of you trigger a massive computation in the Google data center. So what happens when you ask Google something? Can someone tell? So when you ask a query, what happens? You can type it in the chat box, Hardik, maybe. What happens when you type goes through all the web pages and display relevant results? It will search for that web page on their index. We will get possible answers to the queries. It checks on the database. It sends out query on internet, searches the whole database. Okay, nice. Crawl. It crawls the internet for similar keywords. Huh? Not really, Shrikara. Not really. See, what happens is if you, so you issue a query, okay, so you ask something, some query, you want to know about AAAT CHD program. This is the query that you have. And when you ask this query, what happens is this query goes to Google Data Center. Google Data Center contains so many, lots of machines. These are all computing systems. Tens of thousands of machines will be present. So this query that you ask, it gets distributed to all these machines. The query that you ask, the query that you ask, it goes to all or some subset of machines. It goes, and the crawling doesn't happen on the fly. The crawling is done separately. So there is another crawl process through which, let's say, this is your big internet. Okay, this is your internet. This internet is already crawled and indexed, and it is stored. So when you make a query, so what happens is the query is issued to multiple machines, and so they search the local database for any web pages which contain those queries, keywords, and then all those results will be sent back to you. Okay, so you send the data to the Google Data Center. You send the query to the Google Data Center, and the results will be sent back to you. So this is what is called as a massive distributed computing system. Okay, so there is a distributed, because there's a collection of machines are handling your stuff. Distributed computing system. It's a collection of computers. It's a collection of computers. So the hardware of this data center is all these servers that are sitting there, servers, desktops, whatever these machines. And the software is the search algorithms and the merge algorithms that run on these machines, that they constitute the, the software that runs on this data center. So any computing system, it has these two things, a hardware and a software. Crawl means, you kind of, all the web pages, there will be some program which systematically, like for example, when you manually browse, you come to AAAT page, and from there you go to CSC page, you go to ECE page, you go to CHD page, so on and so forth. That process is automatically, you can write a small program which automatically visits all these web pages, and whatever the data that is present on these web pages, it will store it locally in its database. That is called as crawling. Is crawl the traversing algorithm, kind of, we can say it's Don't worry, Gaurav, it's just get a high level picture. So you give a query and the query goes to the Google data center, and the data center contains multiple machines. That query is distributed to these machines and they give results, and all these results are merged. So I am not expecting you to understand the details of this, but broadly my point here is the query that you ask is being processed by a large collection of machines. And this is what is called as a distributed computing system. And you merge all the results, and Google, the software on the Google data center, it merges all the results and it ranks them and sends the results back to us in that ranking order. So yes, the information is, Purvi has a good point. So the information is distributed between different machines on the Google data center. Samir's question, does it crawling depend on what others searched for it? No, Samir. Crawling is a passive process. You just, Google just crawls the whole internet and gets the whole of the internet information and stores it locally. Maybe it doesn't crawl every minute, like no, for every 3 days it may crawl. Okay, so now you have all interesting questions. So that's, I will stop that line of thinking. Don't worry about the Google data center. I just gave an example to kind of pique your interest. But the primary thing that I would like all of you to appreciate now is every computing system, it consists of hardware and software. Are you all with me on this one particular point? Ignoring crawling and all the other interesting questions you have, we can revisit those questions. But this particular thing, that every computing system, it has hardware and software. This is the idea that I would like you to. And now, if you look at the hardware, there are your hardware, the hardware within your system. I think this is, it can be the hardware within your system, it can be classified into three categories. One is the processor. It's not a category. Every hardware in your computing system, you will have a processor, and you will have main memory, also called as random access memory, and a bunch of IO devices. Any computer and IO devices are keyboard, display, your mouse, your mic, your webcam, all these things, they constitute IO devices. Now I have a question for you. I guess all of you bought laptops recently. Could you put in the chat box, what is the processor in your laptop? What's the processor? Ryzen 7, i7, i5, M1. Nice, M1 Pro. Ryzen 5, Ryzen 7. Are there laptops with Ryzen 7 also? Ryzen 9, Siddharth. Is Siddharth is all into gaming or what? No, is Ryzen 9, you require Ryzen 9 for gaming? Or I don't know, it's okay. Programmers here. It came for okay, good, nice. Okay, I'll have one interesting questionnaire at the end of today. I will circulate. Yeah. Good. So any computing system, it has a processor, it has main memory, and a bunch of I/O devices. And if you take a little bit, zoom in a bit, you can see in this picture that you have your processor, and your processor is connected to your main memory via a memory controller. And there is, and it is also connected to your to the I/O devices on the system via some bus. Let's call it a system bus for the time being. I would like to draw your attention to the memory. So your memory is, we think of our memory as a sequence of bytes. Okay, our memory, we think of our memory, we view our memory as a sequence of bytes. So this is byte 0. Maybe I should use different color. Yeah, this is byte 0. This is byte 1, byte 2. So on the right hand side, you see 0x0, 0x1, 0x2, 0x3. So they are the associated addresses in hexadecimal form. So don't worry about it. So your memory, logically, we look at our memory as a linear array of bytes. And every byte is consists of 8 bits. Every byte is divided into 8 bits. So B0, a bit can be either 1 or 0. B1, B2, B3, B4, B5, B6, B7. So every byte, it consists of 8 bits. A byte is a sequence of 8 bits. And every bit is either a 0 or a 1. And this bit B0, which is there here, this bit B0, it is called as a least significant bit, which is on the right-hand side, least significant bit, LSB. And B7 is called as most significant bit, MSB. Least significant bit on the right side and the most significant bit on the leftmost side. So in terms of hardware, let's see. So there are questions why a byte is 8 bits. It's a convention that is being used. Earlier, people worked with 4 bits also. It's called as a nibble. So 4 bits. People tried things, but finally they settled with 1 byte as a bit is a unit of information. Okay, you can like, for example, whether you are present, let's say I want to encode the information, whether you are present in today's class or not, I can store it in the computer using 1 bit. 1 means you are present, 0 means you are not present. Or like, for example, you want to maintain information about whether it rained or not across 365 days of the year. For every day of the year, we will have 1 bit, and 1 means it rained on that day, 0 means it didn't rain on that particular day. All right. So don't worry about what system bus is. It's a collection of wires. Just think of them as electrical wires, which connect the CPU with the other components that are present in the system. So what is important here, I would like you to appreciate is, let's focus on this bits and bytes business because it is very fundamental. So your bits, the most fundamental entities in your system are bits. And every bit, it's either 0 or 1. In terms of physically speaking, you can represent these bits in different ways. So can you suggest me a few ways by which we can represent these bits? Can you suggest me some ideas on how we can go about storing these bits? Bulb on or off? Yeah. A physical means of representing bits. High voltage, low voltage. Binary system is not a physical representation. True or false is also not a physical representation. South pole, north pole. Good. A physical means. A bulb is a physical means, right? So it is, the bulb is on LED, there's an LED, and if LED is on means it is 1, if it is off means it is 0. Burned or not burned, black or white, awesome. Empty or full, switch up and down. Okay, capacitor, charge on the capacitor or no charge on the capacitor. So there are different physical, vertical or horizontal, excellent. Okay, so there are difficult physical means for realizing the bits. But what we do is, we kind of ignore, and so in computing systems, every bit is realized using a circuit with consists of transistors. Okay, so in systems, there are different ways of doing it, but we use some transistors, perhaps capacitors. So there is some physical means for storing this 1 bit of information. So this the very powerful idea that I would like you to appreciate is this notion of abstraction. That is, we are just happy with zeros and ones, and we don't care about how these zeros and ones are represented or stored or held at the hardware level, at the physical level. So in this course, we take the abstraction of the bits. We start later, let's say, for example, when EC students do a course on VLSI, they worry about how you represent these bits. Okay, but right now in this course, we have this abstraction. Bits are the fundamental abstraction for us, 0 and 1. And so a collection of bits together constitutes a byte, 8 bits. What is a byte? A byte is a sequence of 8 bits. Rohan says, what is the idea of abstraction? So the idea of abstraction is you're working with, you're not, you don't worry about the underlying mechanics. Okay, you just take it, hey, 0, either this is 0 or 1, and you fix your thought process. Or so like bits are the basic mathematical entities that are given to you. How they are realized underneath, we will not worry about it. Okay, so let me see if is there any other interesting. Can someone give an alternate example for good? Yeah. Thank you, Argya. So when we drive a car, so there is this brake, there is accelerator, there is clutch, etc. So internally, what happens when you press an accelerator, or how the gearbox works, all those things you don't worry. You just, or like, for example, the simplest thing is the steering. Steering is a very good abstraction. So you turn it to the right, it goes, you turn right, you turn it to the left, you turn left. But internally, how that thing happens, when you turn right, no, it moves internally to the right. We don't know. Okay. So engineering is all about abstractions. Same goes for a washing machine mixer. That's true. All engineering is abstractions. How do you create the right abstractions for the end user so that they can get their job done without worrying about underlying mechanics? You know, some of you who are familiar with automatic transmission and manual driving in cars, you know, like in automatic transmission, you don't worry about changing gears and all. You just press the accelerator and then it goes. But if you are driving manual, you need to worry about in which gear I should keep and releasing the clutch and all that. Yeah, Scooty versus no. In Scooty, it's an automatic transmission. But if you have some maybe some other big bike, then you need to worry about gears and all. So Scooty provides a nice abstraction for you. That's why it is super popular. Okay. So if you can provide nice abstractions to end users, then you can make tons of money. Okay. So great. So nice. So yeah. So now we take bits as abstraction in the sense we don't worry about how they are internally represented using transistors, capacitors, or whatever it is. And then a byte is a collection of 8 bits. And your memory, your RAM or main memory, it is a linear array of bytes. We look at it as a linear array of bytes. But underneath, your memory could be represented as a collection of memory banks and lots of stuff can go underneath. But from our perspective, we just think of memory as a linear array of bytes. So this is your linear array of bytes. It just keeps going. So you have your CPU here. And here you have your memory. This is a much more simplified picture. You think of your memory as a linear sequence of bytes. Okay, and every byte has an address. This is byte 0, byte 1, byte 2, byte 3, so on and so forth. Are you all with me here so far? Doing all right? So you should use abstraction as a learning tool also. Sometimes when you get stuck on something, try to abstract away the details and get the essence of it, and then you can move forward. Don't worry about the memory controller. Memory controller is a circuit through which you can access the RAM. Okay, main memory. So there is this memory controller, which I didn't draw. This is the memory controller. So let's not worry about it now. We don't need to. It's not that important. But the point is CPU and memory, they interact with each other. So Anusha has a question. Anusha, I will take that question later, not today. Some few classes later, I'll take your question. So now I have a question for you. What is the size of the RAM or main memory on your computer? 32 GB, 8 GB, 8 GB. So 8 GB seems to be the common case. 16 GB, okay. Great, 8 and 16 GB. Some of you, I think 1 or 2 have 4 GB, but it's good these days to have at least 8 GB of RAM. Okay, good. So now, so what is this GB business? We will see now. So what do we have? So if we have 2 power 1024, 2 power 10, So 2 power 10 bytes. What is 2 power 10 bytes? So 2 power 10 bytes is 1 kilobyte. 1 kilobyte. And what is 2 power 10 KB? 2 power 10 KB is 1 megabyte. And what is 2 power 10 MB? 1 gigabyte. And what is 2 power 10 GB? 1 terabyte. So some of you know these ideas, but others who who didn't see these things before, don't worry, okay? It's just, now you know. You don't know before, now you know it. So it's not at all a big deal. So 2 power 20 bytes, 2 power 30 bytes, 2 power 40 bytes. 1 kilobyte is 1024 bytes, not 1000 bytes. So all the lecture, when when I post all the annotated questions, everything will be there. Pradham Mishra, why only 1024? Because 2 power 10, you will see why it is the case, okay? We will, it's an interesting question. We will say why 1024 and so 2 power 10 terabytes is 1 petabyte. Okay, 2 power 10 is approximately 1000. So why not 10 power 3? So it is, we do everything in base 2. So why we do in base 2? Because we store information in base 2. So because of that, instead of getting 1000, we get 2 power 10. Okay, 2 power 10 is closest to 1000. 1024. Since, yeah, I will, yeah. So here there are 2 points I would like you to understand. Just to kind of again resync with those of you who may be getting lost. I only want you to understand 2-3 ideas here. The first one is bits from a byte is a sequence of 8 bits, and your main memory is or RAM is a linear array of bytes. This is and every byte has an address 0, 1, 2, 3, 4, so on and so forth. This is one. The third idea is this very simple thing, that 2 power 10 bytes is 1 kilobyte, 2 power 10 KB is 1 megabyte. So you just remember this: 2 power 10, 1 kilobyte, 2 power 20, 1 mega, 2 power 30, 1 giga, 2 power 40, 1 tera. You just remember this. Okay, this is important. Are you all with me here till this point? Simple. So here, one idea I would like you to appreciate and recognize is, so you know that every byte is a sequence of bits. And let's say, look at bit B4 of byte 2. If you want to access, let's say in this particular position, you are storing whether, let's say, Sai is attended today's lecture or not. So this bit B4 doesn't have any address. The CPU fetches the whole of the second byte, and then it internally makes this bit to 1 or 0. So Yeah, we are talking about the addresses. Every byte has an address or a name. So the 0th byte, first byte, second byte, third byte. But before within the second byte, it doesn't have a direct name. So let's say if the processor wants to manipulate this particular byte, this bit before, then it will take the whole of the second byte and then changes the bit before in the second byte. What I'm telling is these addresses, each of these bytes, the bits within a byte, they don't have a name. Think of this. This is the example. So if your memory is a collection of, it's a linear array of bytes. Let's say if your memory is a colony and every house in the colony, it has it's a byte. So every house in the colony has an address, but a room within a colony doesn't have address. Do you get the point? The houses within the colony, they have the address, but every room within a house doesn't have address. So when you write, so as a programmer, you know specifically that bit before of byte 2, I am using this for particular purpose. So question, why not? So let's see if every room in your house has an address, what will happen? Yeah, it's a mess. Too many addresses, okay, associated with your house. There will be 5 addresses or 6 addresses, and you also need to worry whether your bathroom needs an address or not. So, sorry. Yeah, so yeah, so Manav has this question, why B0 is least significant. I never thought about that question. But let's say instead of, I'll give a quick analogy in decimal numbers, 102, 102 is, if let's say, who asked you this question? Why is it called as least significant or? Yeah, so do you want 1 or do you want 2? This is a decimal number. This is not a binary number. Just look at 102. What do you want? Do you want 100 rupees or do you want 2 rupees? This one has a greater value. As you keep going, to the left, it has greater and greater value. So you want 2? Yes. So I should make a good business with you so that you all the time take least significant bytes or bits. I'll take the most significant bits. Okay. You understood, right? So this is, I am just guessing. I never asked this question, but so 2 is least significant. In terms of decimal numbers, let's say for the time being, this is least significant digit LSD. This is the most significant digit. No, I'm saying in the bits you have seen, so B7 to B0, this is called as an MSB, most significant bit, and this is called as an LSB. This is the least significant bit. The question is why? So there is a value associated with each of these bits. We will see later. For the time being, we'll revisit this question. Okay, let's not, I think all of you are thinking a lot. So we'll revisit this. You'll get it later. Just for the time being, think of it as a convention. Okay, so last couple of minutes of discussion, I want to flush. There are 2 things I want you to remember from this explanation now. B0 to B7, it's a convention that we just call B0 as LSB and B7 as MSB, number 1. Number 2, if you take a bit within a byte, it doesn't have an address. A byte has an address, but a bit within a byte doesn't have an address. That's all. Are you all with me on these 2 points? Yes or no? Good. Let's keep going. So now, again, so this is very interesting idea. So any program that you would like to execute, the instructions of that program should be available in the main memory or RAM of your system. And what the processor does is it fetches an instruction of the program. It decodes that instruction. Like the instruction could be an add instruction, subtract instruction, whatever it is. And then it executes that instruction. Once it decodes that instruction, it executes the instruction and it repeats. This is what is called as a fetch, decode, and execute cycle. This is fetch, followed by decode, followed by execute. This is what is called as a fetch, decode, and execute cycle. So this process keeps on continuing, fetch, decode, execute, fetch, decode, execute. And that's what your processor does. So for example, can you now check in your, you are using the Zoom software. Can you tell, put in the chat box, how much memory is occupied by your Zoom software? Because all the instructions of the Zoom program are loaded into the memory. Can you check in your system and tell me how many? 166 MB, 280 MB, how many instructions? How much memory is occupied by your Zoom? 355%. Okay. Great. So when you say 2.6%, that Aryan, it depends on how much overall memory you have. So around 250 to 300 MB is occupied by your Zoom program. The processor fetches the instructions from the memory. Remember, the instructions are present in your memory. Your program instructions are present in the memory. So this is the execution model of your system. You can use top here, genome system monitor. Great. No, the instructions doesn't come from IO devices. We will see that flow later, but the instructions of the program are present in the memory, and your processor fetches these instructions, decodes them, and executes them. The CPU decodes the fetched instructions, and it understands what that instruction is, and then it executes them. Okay. Are you all with me on this one? This is a very important thing, that for your program to execute, the instructions of the program should be in the memory, and this fetch, decode, execute cycle is carried out by the processor ad infinitum. So now, with this as the background, so if you think of your program, this is a course on computer programming. Your program consists of a sequence of instructions, and perhaps along with it some data also. And every instruction is a sequence of 1 or more bytes. And every byte is a sequence of bits. So your program is a sequence of instructions, and every instruction is a sequence of bytes, and every byte is a sequence of 8 bits. So your whole program is a sequence of bits. So when you download a program from Zoom or any other software from internet, that program is transmitted as a sequence of bits. Or when you store a program in your computer, we'll talk about it in a while, it will be stored as a sequence of bits. A program is stored as a sequence of bits. It is retrieved as a sequence of bits. So everything on your computer, be it data, program, whatever it is all sequence of bits. Now, so when you install the Zoom program, your Zoom program is initially residing on what is called as a hard disk of your system. Your Zoom program is initially residing on the hard disk of the system. Okay, so your Zoom, your Chrome browser, or whatever the browsers that you are using, they are all residing on your hard disk. But when you execute the Zoom program by double-clicking the Zoom icon or whatever the mechanism that you have in your computer, what happens is the instructions of your program, the instructions of the Zoom program, so they will be the instructions of the Zoom program, they will be loaded from your hard disk into the main memory of the system. This is called as a primary memory. RAM is also called as primary memory. This is also called as secondary memory structure. And the very important difference between the primary memory and secondary memory is primary memory is volatile. That is, if you remove the power supply, all the contents of the memory is gone, but the contents that are written in your hard disk, they still persist even when there is no power supply. That is how you are able to save all your data, programs, everything on your computer. So when you give a program for execution, the instructions of the program are loaded into the memory by the operating system software from the hard disk. And then the processor starts executing the program. Fetch, decode, execute happens between the CPU and the processor. If a program is just remaining in a hard disk, it's not under execution. It is not executed. It's not. So this idea is important that when you have your program, when you install all your software, it's all there on your hard disk, persistent storage, non-volatile storage. When you remove the power supply, the program, instructions, data, everything is still there. But in order for you to execute the program, the instructions of the program needs to be loaded from the hard disk to your main memory. And when we come to hard disk, there are two kinds of hard disk structures. One is based on magnetic disk technology. The other is based on solid state technology, HDD and SSD. SSD stands for solid state drive and HDD stands for, I think, hard disk drive. But generally we just say hard disk, which means be it HDD or SSD. So again, this is yet another important idea in today's lecture, that programs, when your programs on the disk doesn't mean anything, they are sleeping, they are not active. When you give a program for execution, it becomes activated, the instructions of the program are loaded into the memory. Let's see the questions. What is access time, SSD? So access time is in order to access a byte of data from, if the processor wants to access a byte of data from the RAM, it may take, few nanoseconds. But if it has to access a byte of data from the hard disk, secondary storage structure, it requires few milliseconds. The array on the right is RAM. Yes, that's true, Gaurav. Yeah. And there's a question how the program goes from HDD to RAM. We will see this in the next class apart. In the next class, we will see how the program gets moved from HDD to RAM. Why is the access time not uniform for hard disk? Good question. What is virtual RAM? Yeah, RAMs are faster than SSD due to their physical properties. Just to give a quick question, a quick answer to the question, no, what is the, let's say, did you ever, have you ever seen audio cassettes with a magnetic tape on it? So what happens, no, if you want to, in olden days, no, when I was at your age, if I want to fast forward a song and go to a particular, want to play a particular song, then they have to roll. So the time required to access a particular location on the tape, it is not uniform because it depends on where the current head is. So if it's a nearby point, you can quickly access it. If it is far off, then you have to roll much longer. The same story in the case of HDDs, hard disks. Okay, instead of rolls, they have a disk. And depending upon where the read-write head is, so let's say this is your storage disk, and you have what is called as a read-write disk, read-write head. So if you want to read some data which is present here, this kind of rotates, this disk rotates. Oh, gramophone record, So because of that, the access times vary. But in the case of memory, the physical technology used to realize memory, it almost makes we can access any byte with the same access time. Gaurav finally got it. Gaurav, yes. What Gaurav summarized today's last 5 minutes or 10 minutes of lecture. Data is loaded from the hard disk to the RAM and then to the CPU for execution. Yeah, approximately. Muskan, what does device controller hub do? Let's not, we'll worry about it later, Muskan. Because, the devices, they have different electromechanical properties. Mic has some kind of interface. Your speaker has some other kind of interface. Your mouse has some other kind of interface. So there is a lot of variability in IO devices. So we need some kind of intermediary stuff to kind of regulate access to all these things. Samir has an interesting question. Samir, no idea. Samir, I'm a computer scientist, not a neuroscientist. Aryan Bansal wants to know about grading system. So these are the main ideas in today's lecture. It is 101. So we'll stop here and